Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ade Bakir bin Amir, representing Group G for May 2026 IDP projects. So for this semester, we are tasked to design a reactor separator system for methanol production plant. Next, let's get to know our members. So we consist of 5 members, starting with me. My name is Aida Kevin Ame with the student ID 220111694, and then Muhammad Amirul Zidan bin Muhammad Nasir with the student ID 24004996. Next will be Siti Nurhaida Nadia binti Saad with the student ID 22004218. Next will be Nur Zari Zulaika binti Norizan with the student ID 24000075. And last but not least, Nur Anisa binti Bohan with the student ID 24000117. So that's all for our members. Alright, before we dive into the much more complicated parts, we dive into the background studies, problem statement, and what we are doing on the two key areas. So, what is the background studies? So, basically, methanol is an essential platform chemical for fuels and manufacturing. However, the conventional production relies heavily on the fossil fuels, in which releasing significant amounts of carbon dioxide into our atmosphere. So how do we counter this? Our project basically proposed an integrated reactor separator system to produce around 100,000 tons of methanol per year via the direct hydrogenations of captured CO2. But the challenge is that CO2 hydrogenation is limited by two key areas, which is the reaction equilibrium and the reverse water gas shift side reactions. And also, the effluent contains water and unreacted gas that must be purified first to hit the target purity of 99.5%. So how are we going to make this work? So we include two key areas into our projects, or integrated two key areas into our projects. So the first one is the reaction engineering. So we select the production routes, catalyst, and reactor. Then we determine the operating conditions and reaction kinetics. And lastly, we perform material balance and evaluate the reactor performance. So moving on to the separation process, we identify the crude methanol compositions. Then we design an absorption system for the methanol purifications. And last but not least, we estimate the absorbent requirements and propose a regeneration strategy. Alright, moving on to our scope of study. So for this design, we strictly focus on the conceptual reactor separator system, or specifically covering the reactor sizing, material balance, and absorption column design, but we exclude the detailed mechanical and economic analysis. So for the design basis, the plant basically operates around 330 days per year to reach the annual targets of 100,000 tons per year, in which this translates to the hourly production of 12.63 tons per hour, or in other words, 394.07 kilowatt per hour, with the target purity of 99.5%. So to make this capacity, we actually selected the direct carbon dioxide hydrogenation routes. What Why it's not the other way? The reason is simple. This pathway directly utilizes captured carbon dioxide to support the CCUS initiatives, integrate wells with the renewable energy, and leverages commercially proven copper, zinc oxide, and alumina catalysts for high industrial feasibility. Alright, next let's examine the reaction stoichiometry and kinetics. So our process involves two competing pathways. So the first one, the main methanol synthesis, is an exothermic reaction which favored by the moderate temperature and high pressure, but it competes with the endothermic reverse water gas shift side reactions, in which produces unwanted carbon monoxide and subsequently reduces the methanol selectivity and increase our downstream separation loads. So in order to optimize our yield, we establish operating conditions of 250 degrees C and the pressure of 50 bar. This temperature provides a balance by limiting the side reactions, while also the high pressure drive the equilibrium towards the methanol formations. And for the gas feed, we also feed the gas to a 3 to 1 stoichiometric ratio of hydrogens to carbon dioxide. So for the reactor sizings, we adopted the Van Buscher and Froment kinetics model, in which utilizing a copper, zinc oxide, and alumina catalyst, we assume the steady state and the isothermal gas phase operation without pressure drops, in which allowing us to accurately apply standard Crête laws.
Now let's go to the material balance part. This slide shows the design basis used for the reactor material balance. The methanol plant is designed to produce 100,000 tons per year with a target purity of 99.5 weightage. The plant operates 330 days per year, equivalent to 7,920 operating hours. Based on this production target, the methanol production rate is 12.63 tons per hour or 394.07 camel per hour. Since the reactor is designed with 90% of methanol selectivity, the reaction extent is 437.86 camel per hour. Using the stoichiometry feed ratio of 3:1 for H2 and CO2, the required reactor inlet flow rates are 2,189.32 kmol per hour of CO2 and 6,567.97 kmol per hour. So this value from the basis for the reactor design calculations. Now this slide presents the reactor material balance result. The stoichiometry table was developed based on the main methanol synthesis reaction and the reverse water gas shift set reaction. From the calculations, we get the reactor outlet contents of 1,751.46 kmol per hour of CO2, 5,341.95 kmol per hour of H2, 394.08 kmol per hour of methanol, 437.87 kmol per hour of water, and 43.79 kmol per hour of carbon monoxide. The outlet gas composition was then calculated using the mole fractions and the ideal gas equation at 250 Celsius and 50 bar. The outlet composition are used as the feed for the downstream methanol purification process. Now, this slide summarizes the reactor sizing and performance. The reactor selected is a multi-tubular packed bed reactor operating at 250 Celsius and 50 bar using a copper or zinc oxide or aluminum oxide catalyst. Based on the reactor design calculations using Simpson one-third numerical integration, the required catalyst weight is 10,034 kilograms, corresponding to a packed bed volume of 5.65 cubic meters. The reactor achieved the target 20% single pass CO2 conversion, while recycling the unreacted gases increased the overall CO2 conversion to approximately 96%. So this reactor design provides efficient heat removal, maintains a catalyst stability, and is suitable for a large-scale industrial methanol production.
Moving to our reactor performance analysis, this slide shows the relationship between the single-pass carbon dioxide conversion and product selectivity in our multitubular PBR. Looking at the plot on the left, we can clearly see two inverse trends as conversion increase along the x-axis. Methanol selectivity, blue line, drops from 96% down to 81% at 30% conversion, where carbon monoxide selectivity, red line, steadily rise from 4% to 19%. So this trade-off is driven by thermodynamic equilibrium and competition from reverse water gas shift reaction. Pushing a single pass conversion higher via higher temperature or longer residence time, it promotes side reaction that form unwanted carbon monoxide instead of methanol. So this presents a classic trade-off where high conversion we will sacrifice selectivity while low conversion increase gas recycle burdens. So to optimize this, we identify a target design point at 20% single pass conversion where conversion of carbon dioxide at 0.2. Here we preserve a high 90% methanol selectivity while capping carbon monoxide selectivity at 10%. So couple this with our recycle load, this achieve a high overall efficiency without compromising purity.
Moving on to the separator system, before designing the purification system, we first identified the chemical species present in the crude methanol stream leaving the reactor. Based on the reactor outlet composition, six major components were identified, which are methanol, water, carbon dioxide, carbon monoxide, hydrogen, as well as methane. Among these components, methanol is our desired product, while water is the primary byproduct formed during methanol synthesis. Carbon monoxide and carbon dioxide are residual reactants due to incomplete conversion. Hydrogen is supplied in excess to improve methanol production. and methane behave as an inert component originating from the syngas feed. For the concentration calculations, several assumptions were made. We assume that the gas's steady state operation, ideal gas behavior, negligible pressure drop across the cooler, and no further chemical reactions after the reactor. The stream is first cooled to 30 degrees Celsius at 3000 kilopascals, providing suitable conditions for evaluating the composition before purification. Using the ideal gas equation, the concentration of each species was calculated based on its mole fraction. These concentration values serve as the design basis. After identifying the composition of the crude stream, the next step is to design a purification system capable of producing industrial-grade methanol. To achieve the required methanol purity of at least 99.5 weight percent, we propose a fixed bed adsorption purification system. The purification process begins with a feed filter, which removes suspended particles and catalyst fines that could damage or fool the adsorption bed. This helps maintain stable operation and extends the service life of the adsorbent. Next, the stream enters the fixed bed adsorption column. In this unit, water and trace impurities are selectively adsorbed onto the adsorbent surface, while methanol passes through the bed with minimal loss. This pollution step is important because even a small amount of water can reduce methanol quality and affect downstream applications. To allow continuous production, two adsorption columns are used. While one column operates in adsorption mode, the second column undergoes regeneration. The columns alternate operation so that purification continues without interrupting the process. Finally, the purified methanol is collected in the storage tank where it meets the required industrial specification. To confirm that this purification system can achieve the required product purity, we perform a preliminary material referring to the previous slide. First, the reactor produces approximately 12,626 kilograms of methanol per hour. Since the target purity is 99.5 weight percent, the total product flow rate was calculated based on this methanol production rate. For this preliminary design, we assume that the feed entering the absorption column consists of 97 weight percent methanol and 3 weight percent residual water and trace impurities, based on published literature. This assumption represents a methanol-rich stream after the primary separation stage. From the material balance, the absorption unit must remove approximately 327 kilograms per hour of water and trace impurities while retaining the methanol. Finally, an overall mass balance was performed around the absorption unit. The results show that the total mass entering the system equals to the total mass leaving the system plus the impurities retained by the adsorbent, confirming that the conservation of mass is satisfied. These calculations demonstrate that the proposed adsorption system is capable of producing methanol that meets the required purity specification. After establishing the required purification performance, the next step was selecting the most suitable adsorbent, which I will explain in the next slide. Several absorbent materials were evaluated before selecting the most suitable option. Among the available absorbents, 3A molecular sieve was selected because it offers excellent water removal while minimizing methanol loss. This is due to its pore size of approximately 3 angstroms, which allows the smaller water molecules to enter the pores while preventing the larger methanol molecules from being absorbed. Compared with other adsorbents, the 3A molecular sieve also provides high thermal stability, good mechanical strength, and can be regenerated repeatedly, making it suitable for continuous industrial operation. The proposed purification system uses a dual fixed bed adsorption column operating under temperature swing adsorption or TSA. During operation, one column removes water from the methanol stream while the second column is regenerated using heat. Once regeneration is complete, the two columns switch roles. This alternating operation allows continuous production without stopping the process. Overall, the selected adsorption system provides an effective balance between purification efficiency, methanol recovery, and operational reliability, enabling the final methanol product to achieve the required 99.5 weight% purity. That concludes my presentation on the adsorption-based purification system. Next, I will pass the floor to Zidane to present the rest.
Next, I will be presenting about the required absorbent amount of continuous adsorption system. First step, we need to calculate the water mass flow rate, which is we can multiply the value of the total feed flow rate by the 0.055, which is the composition of water, and we get 438.30 kmol per hour. But we need to multiply the value with the molecular weight of water to cancel out the unit, and we get the final value of mass flow rate of water in kg per hour. So as you can see here, our second step is water removed per cycle. This step we use the assumption that for one cycle it operated in 8 hours so that the adsorbent is regenerated. So the value, the formula is mass flow rate of water just now. We just multiply it by 8 hours and we get the value also in kg. And next step is to calculate the adsorbent required. The formula is the water removed per cycle 63167.76 kg H2O divided by 0.2. 0.2 is the value of dynamic adsorption of zeolite 3A, which is one of our assumption. The unit is 0.2 kg H2O over kg adsorbent, and we get the value of 315,838.8 kg. So for the final step in this slide is to calculate the total mass with safety factor, which is 20%. So the adsorbent required, just multiply it with 100% times 20% and we get 1.2, and we get the final answer which is 379,006.56 kg. Next, I will be presenting about the absorption column design. Here we have 3 parameters, which is bed volume, diameter and height. For bed volume, the formula is the total mass of safety factor that we calculate in the last slide. We can divide it by 730 kg per meter cube, which is the bulk packing density of dry zeolite 3A. That is one of our assumption as well, and we get the value of 519.19 meter cube. The second parameter, which is diameter, we can calculate it using this formula, square root 4a over pi, which is we can get the value of 3.02 meter. Our last parameter is height. We can get the value from volume over area of the column, and we will get in our report we will get 72.31 meter. So I will explain about the problem and the solution for this column, adsorption column. The problem is single column is too tall and requires stronger supporting structure. So a solution for this is install multiple adsorption column in parallel. The advantage of multiple adsorption parallel column is it can lower the column height and lower the pressure drop as well, and it is easier in terms of maintenance, and it is continuous operation. Then I will be presenting about the regeneration method, which is we use temperature swing adsorption or TSA method. First step is the adsorption process itself. In this step, water is being adsorbed by the molecular sieve 3A. Next step is the heating process, which is the operating condition is 200 to 300 degrees Celsius. The function is to dissolve back the adsorbed water in first step. The third step is the hot methanol purge. It is to release or wipe away water and impurities in the column itself. Last step is the cooling process. This step is to restore the adsorption capacity, or so that the operating or the temperature will be back to normal operating condition or temperature. Next, we also have other 3 alternative method, which is pressure swing adsorption, vacuum swing adsorption, and steam regenerator. So I will start the advantage for the TSA first, which is It is best for water removal, but the disadvantage is the energy consumption, which is high. For PSA, the advantage is low energy consumption, but it is poor water removal. It is not suitable to remove water. And then for VSA, it requires lower temperature, but it requires vacuum equipment or vacuum pump in this process. So for the last part is method is steam regeneration. The advantage is simple process, but the disadvantage is it introduce additional water into the column.
To conclude, this project successfully presents a conceptual design for a green methanol plant producing 100,000 tons per year via direct carbon dioxide hydrogenation in support of CCUS initiative. Looking back to our main subsystem, for reaction engineering operating at 250 degrees Celsius and 50 bar over a commercial our catalyst, carbon oxide or zinc oxide, our PBR balance kinetic and selectivity at a 20% single pass carbon dioxide conversion. Pair this with a gas recycle loop, overall process conversion reached approximately 96%. For separation, we replace energy intensive distillation where a zeolite 3A molecular sieve system using temperature swing adsorption leveraged kinetic size exclusion where 3 angstrom pores absorb 2.65 angstrom water molecule while excluding methanol. This to purify the product up to 99.85% industrial grade purity. So operational recommendation to overcome practical single bed head constraint from high water loading. Future work also should implement a multi-column parallel arrangement or an upstream pre-dewatering flash drum. Thank you for your attention.